Okay, let's go.
Last time we ended with some examples. There's probably like a mathematical form or something. I don't think these three boards work well together. Like one is always going to be like out of sync, whatever. Last time, we saw the notion of a separable differential equation. So last time, we saw a technique of separation of variables. ODEs where this can work. They're called separable. Let's actually make an official definition. First order is separable if it can be written in the form something like f y dy equals g of x dx. Where f is a function derivative of y, g function derivative of x. X is the independent variable, and y is the dependent variable. And of course, the actual variables themselves matter less than the idea. The idea is you can separate whatever two variables show up, whoever is independent versus the dependent, and we can write them in this particular fashion. I want you to just note, pay attention, that you can imagine that a multiplication is here. So the f of y cannot be separated from the dy by a plus or a minus sign. Similarly here, these guys have to multiply. And so that's the idea. You can separate the guys so that we have the differentials paired up with functions corresponding to their variable. And again, the x and y here are just examples. They're not. This idea applies across variables, so it could be x and y and t and v, mu and theta, it doesn't matter. And yeah, Greek letters are coming back, so expected. Remember, last time I taught this, I don't know, it's an 8 a.m. class. Okay, there's no excuse, but it's fine. I was going through a proof where there were like a bunch of Greek letters all over the place, and I kept calling a Greek letter by the wrong name. So I think it was like 5, but I kept calling it psi or something else like that. So like throughout the whole lecture, I'm calling this letter by the wrong name, and afterwards this Greek person came up to me like, "You're driving me crazy, man." It's like you were writing down B on the board and kept saying F. What is wrong with you? Like, what the is? Yeah, it's pretty hard. So, he's watching. I'm sorry. I don't know why I'd be watching again, but you know, everyone has to be apologized. apologizing these days. So just in case, like 20 years from now, like a Twitter storm comes up, you know, video surfaces of Jhevon disrespecting the Greek people. Just know it wasn't intentional. I did not.
I like the Greek.
Oh my God! Now it's I apologize to the Greek people. Okay, I'll try to probably use less Greek letters next time, so don't worry about it. So we did a bunch of examples. I'm not going to do more examples of that. I will make the following important idea. I said this, I'm not sure I wrote it down, so I'm never going to write it down this time. Remember, sure, this course, you have to remember all your calculus, you have to remember how to integrate, differentiate, do all that stuff. There are some prerequisite skills, but as far as what this class is about, it's about methods, right? So again, kind of like Calc 3. So pretty much what you need to zoom in on, the minimum you need to walk away from this class understanding is that, okay, differential equation looks like this, I can do that. Differential equation looks like this, I do that. Differential equation looks like this, I do that, right? That's the idea. If you can do that, you're okay. If you can go better, that's icing on the cake. But it's about methods. And now when it comes to methods, an issue automatically presents itself. You will automatically start to run into issues where you're not going to always know when to choose which method, right? So that's going to be important. So in like Calculus 2, for example, you learned a bunch of integration techniques, but if someone throws a random integration at you, then you have to, sometimes you have to guess and check. However, just like in Calculus 2, there's a certain like order of priorities here. There's a certain kind of thing you look for first and second and third and fourth, etc. Right? So, given a random integral, the first thing you're going to try to do is try to use a basic rule. The basic rules are just the rules that tells you how to integrate each function. Like, okay, there's the integral of x to the n equals x to the n plus 1 over n plus 1 plus c when n is not minus 1, etc. So you have all these lists of basic rules, and that's the first thing you're going to try. If that doesn't work, the second thing you're going to try is to simplify the function to see if you can get those basic rules to expose themselves. If that doesn't work, you're going to do substitution. Can I substitute something to make it less complicated where its derivative is somewhere else in the function? And after that, you start to think integration by parts. Maybe if you see fractions, you start to think partial fractions. But there's like a hierarchy, right? You think basic rule, oh no, can I simplify to use a basic rule? No. Substitution? No. There's an order in which your brain is supposed to think. So really in Calc 2, you never should approach a problem randomly, even though it kind of feels like you're doing that. There is a way you're supposed to be thinking. Now, as far as that is concerned, separation of variables happens to be one of the first things that you should be thinking, especially when we're dealing with first order ODEs, right? So there are some differential equations where you can kind of just see what the answer is by inspection. I'm not going to put that on the list because I'm very rarely going to ask you things like that. But then the next thing you want to look for is separation of variables, especially when you're doing first order ODE. That's like this substitution of integrals, right? So it's one of the easiest techniques that's just a step above being brain dead. So it's always the first thing you look for, because if it works, it's going to be the easiest thing to work, right? So you always check for that first. So if I throw a random integral at you, the first minute, is it separable? That's kind of where your brain should go in the first place. And then when I teach you other methods, I'm going to tell you, okay, you probably want to think of this method before that method, and we'll start to lay out the order. But separation variables is one of the first techniques to consider replacing a random first order ODE. More strategies for But just know that that thing that I taught you last time is going to be something that you're always looking out for. And what else did I want to say? Well, I wanted to say something, but I forgot. Probably is important. Let's move on. Separation of variables means that. Okay, so we're going to move on to another way. We're still in chapter 1. So chapter 1 talks about another way to here. And typically you can apply this to things that are higher than first order, but typically you'll see it in this class in the first order case. If you're higher than first order, the differential equation has to behave a certain way where a certain kind of substitution can be used. But anyway. So another thing that this talks about in chapter 1 is the idea of the direction field. Now this might remind you of a vector field from 392 if you happen to be taking 392. The idea is the same. You're going to look at the space, usually the 2D space if we're first order ODE. And you're going to plot things on that space, and they're going to indicate to you what's going on in the environment, and hence they can indicate to you what is going to be, what the solution might look like. Now, direction fields, you kind of use these when finding an analytical solution. You can't actually solve for it by hand and get a nice answer. It's kind of out of reach. Like I said, most differential equations, they're really tough, and you don't actually know a nice method to solve them by hand. But direction fields provide another way. If you have this really weird first order ODE, and you can't integrate anything, or you don't know how to integrate anything, or you don't know how to approach it, direction field is one option to give you some sort of answer. So let me show you how a direction field would be used with, again, a simple example, just so you don't get lost in minutia here. So we saw that, we know how to solve that by inspection and by separation of variables, but let's suppose we didn't know all that or didn't remember all that. One thing you can notice is what this actually says, if you were to actually think of this like you were a Calc 1 student. This basically says the slope is y, more specifically the slope of the tangent line. Now, once you can read a first order ODE as that sort of statement, as it's literally a statement about how to compute the slope of the tangent line, then you can start to get a lot of nice things out of that. So for example, if I were to actually start plotting some of these here on the Cartesian axis, I'm going to start plotting a bunch of tangent lines. Let's do that. So, along the x-axis, what would my tangent lines look like? So let's say I pick this point. What would be the tangent line moving through that point? Horizontal. It's horizontal, right? Because on the x-axis, y is 0. So usually if I select points here along the x-axis, and just draw a little bit of horizontal lines just to represent an infinitesimal portion of the tangent line that would occur there, I would see a bunch of horizontal lines. Then I can move up to the level of y equals 1. And what would the tangent lines look like at that level? Well, they all would have slope 1. So I can have a bunch of infinitesimal tangent lines here, and they're all slanted that way. And then I might move up to 2. And along that level, what is the slope of the tangent line? Well, it's 2, because the slope is whatever the y is. So that will be a little bit steeper. And then if I move up to the level of 3, and I plot along that line, that would be even steeper. if I were to say go down to y equals minus 1, then I'd have a bunch of tangent lines with slope minus 1, so they're moving down as they go from left to right. Or at minus 2. They again go down, but a little steeper. Now once you do this, you create almost a sort of vector field of little infinitesimal tangent lines. And you start to see a kind of pattern, right? This differential equation colors the plane into a certain suggestive pattern. And so someone might say, okay, this is how this differential equation makes the 2D plane look. What if I wanted a solution to this guy that passed through that point over here? Now what would you expect that solution to look like? Well, you kind of look at this as the environment. You notice here what's happening is, if you think of this as like a pond or some sort of flowing system, it will kind of push the point along a curve here. Right? And you can kind of see something just being traced out here that's following all the tangent lines. And you get something like that. Or someone might say, what about if I want the solution that passes through the point over here? Well, again, there's a pattern that you can follow. And you'll start to know that, oh, those look like an exponential. So this is like some sort of c e to the x. Right? You can see the curve here, right? Which is kind of very suggestive. And either that will actually give you some ideas as to what the answer is, or at the very least, if you're using a computer to help you out, which chances are if you're doing this method, you will be using a computer to help you out. You can just have your computer approximate it with some nice function. Just say, okay, take a whole, like 100 points and just make up some curve that can actually fit it. That's called interpolation. And a lot of times that'll be good enough for whatever you want to solve this differential equation for. So that's one way in which you can kind of start to get a handle on what the differential equation, or what the solution to a differential equation would actually look like. It would be, for this, it would be that green line, given this initial condition. Okay? I'm not going to ask you to do that a lot, but it is an important idea, so I thought I'd mention it. But I can't have you guys all sitting there drawing all this stuff. It's going to be a nightmare to grade. It's going to take forever for you to do, and yeah, it's just not worth it. But it's a thing. It's an option that's out there. A lot of times, you don't know what a differential equation is. You can't actually do the calculus. So literally just let a computer plot points and draw tangent lines for you, and then sketch a picture. Well, it looks almost like this. It's close enough. And you can do all sorts of approximations there, which you would use stuff from Calc 2, stuff from numerical analysis, all that kind of stuff, to really get a better handle on the function. So I thought I'd mention it because it was mentioned in chapter 1, and I did some homework on it, so that's actually helpful. What else did chapter 1 talk about? We did see some models in chapter 1. So, a model is just a mathematical description of a natural phenomenon. And one example that was brought up in chapter 1, I guess to kind of show you, oh, these things are important, is population models. So, there's something, for example, very famous models are things like the Malthus model. Those of you who have taken some biology would know about that. The harvesting model is also pretty popular, which is just really a Malthus model that you affect in a predictable way.
What is the Malthus model?
I'm going to tell you now. So here's what the Malthus model assumes. So we can say let P be a population. And the important assumption is assume P grows proportionally to its current very simplistic assumption, but it's one that tends to make sense. The larger a population is, the more kids they're going to have, the faster they're going to grow, right? Small populations will grow very slowly because they have less children. Large populations will grow very fast because they have more children. And if you just assume the rate of having children is dispersed equally throughout the population, you can kind of say, well, the number of kids is going to be grow in proportion to the size of the population. And that's pretty much it. And pretty much all other factors ignored. And you have a Malthus model. Very simplistic model, but it is useful, it is used.
Doesn't the Malthus model also have like a limit placed somewhere?
A what?
Limit? It usually has a cap on growth.
It can, yeah. So if you're in a situation like this, it will have a cap on the growth.
Is the cap based on like resources or something? Or?
Yeah.
Okay.
The harvesting model starts to attack that kind of scenario more, and there's something called the logistic model, which is probably more accurate than both of these. But these were the two that were introduced in the textbook, so I'm going to talk about them. So now, what does it mean to say that P grows proportionally to its current size?
So it's changing as the size changes? Or?
Yeah, but to grow proportionally to its current size, this is basically saying the rate of change of the size of the population is proportional to the current size of the population. That's the assumption. Notice that if you were to write that assumption mathematically, you get a first order differential equation. Also, you would notice that that is a separable first order differential equation. This means basically dp dt is equal to kp. And of course, p is just the size of the population at time t here. T is time. Of course, now we can actually solve this. Based on that assumption, you can actually get an equation that describes the current size of the population at any time by solving the differential equation. That's what we can do. So what we would do here is separate the variables. Integrating this, we would get ln of p. Integrating that, we would get kt plus c. Raising both sides to the e, we get p equals c e to the kt. And that will actually be how you can find the size of the population at any current time. Given some information, usually like birth rate and death rate, that can help you find the k. That's usually going to be birth rate minus death rate. And given some initial condition, like we know that at this time the population is this much, you can find the c. But that would be how that such a population would be expected to grow. It would grow exponentially, right? So populations never grow linearly; they actually grow exponentially. This basic model actually shows that. When you look at the harvesting model, this is also a very simplistic assumption. It says the population above is being increased or decreased by a fixed amount per unit time. So here's where usually this is how an external factor might be introduced. So you can say, okay, here's a population growing in proportion to its current size, but there are predators that feed on that population, and they kill an average of 3,000 of these guys per year, right? You can actually amend the Malthus model to deal with that situation.
So does the harvest model have any crop stables per year?
Yeah, how many things are lost per year, or maybe even how many things are introduced per year. So let's say there's this population that's growing, but there is something happening over here, and we have a bunch of refugees rushing into this population, and we're measuring the average rate at which people are coming into. And this would lead to this kind of differential equation. So proportionate to its current size, but we're either adding or subtracting some individuals to that population from some outside source. So let's just keep it simple and think of it as plus h. So we would say h is a negative number if the population is decreasing by a fixed amount, and on average, and h is positive if it increases on average. So that is also a differential equation. How would you solve that differential equation? Solve that differential equation. Give you like 30 seconds. We'll see a lot more applications soon, but these were just introduced, so I thought I'd mention them. Is anyone done?
Maybe, I'm not sure.
Maybe. Okay. How do you do it?
I moved RP plus H to the right side. Oh, I turned P prime into dt over dt.
Yeah, and then
move dt to the right
and
side.
you divide it by the whole right side.
Yeah.
Yeah, so you have dp all over rp plus h equals dt. So this is in fact separable. 1 over rp plus h is a function purely of p because r and h are constants. R is going to be like the constant of proportionality or the growth rate. So that's going to be a constant, and then h is a constant because you're assuming it's changing by a fixed amount. And so this is a function of p times dp, that's a function of t times dt. You integrate both. What's the integral of this?
ln of RP plus H. And then the other side is...
No, you're not done.
1 over R.
Substitution, u equals rp plus h, dp equals r, du equals r dp, you end up divided by the r. This one would be t plus c, and so what we end up here is pretty much rp plus h would be equal to c times e to the rt. Right? So I multiply both sides by r. Including the constant c. I had other options too. I could just move this up here, but I decided to multiply both sides by r. And so this becomes equals plus c. And then I'm going to raise e to both sides. rp plus h equals
RC is just a constant, right?
RC RC is just a constant, so that's just, I can move this, to just call it big C. And so now I would end up with my P is going to be C e to the RT minus H divided by R. So it's going to be C over R, H over R. And that will be the equation that helps us get the population. So I could say something like, assume a population grows proportional to its current size, increasing by 5% per year. Hunting decreases the population by 300 individuals per year. Assuming the population starts with 300,000, what would be the size of the population after 10 years? Right, that could be a question. And this is how we solve it. Yes?
How would you do it? Based on it just says it's being increased or decreased by a fixed amount per unit of time.
Yeah, this is just an assumption.
Like, I don't understand going from that to the original, the differential equation. P prime equals R times P equals C.
Oh, the original?
Yeah.
So this is just me using the mouthless model. We're still assuming the population is growing proportional to its current size. So at any given time, the rate of change is a constant times the number of individuals in that population.
So it can
But then I'm saying, besides that growth, more individuals are either being added or taken away from the population at regular time intervals, right? And that's the H.
Yeah.
So my R and my H are constants. R is representing the growth rate, so that's the amount of percentage increase of the population over time, and then H is the amount of influx I'm having. Yeah.
Did you just turn RC up there into just C down there?
Yeah.
Okay.
I'm going to do that all the time. If it's a constant, it's a C.
I have a question.
Yes.
R is a constant, right?
Yes.
Is there a reason that you kept the R in the final answer? Like when you put C equals to RT over R? Does the C kind of follow the R?
You could do that, yeah. You could write this as another constant, and that as another constant. This is, sure. But these numbers, you would actually know them from somewhere else. So this, writing it this way is more suggestive of what the number should actually be. It's going to be the number of things being added or subtracted divided by the rate of the population. That's always what that constant is going to be. So I kind of lose that information if I just call it like a K or something. It's just being a little bit more suggestive.
If we were adding a percentage of the population already, wouldn't H be a percentage? You said 5%, so wouldn't that be?
No, the R is represented by percent. The H is like an absolute value.
Those are the people that are coming in.
Yeah. Coming in or going out, and you're saying on average it's this much people, as in number of people.
Right.
Is he saying and?
And those are the assumptions of the RC model. So it might not fit any population perfectly, but it's a good enough model to make a lot of assumptions, and it is used all over the place. Okay. We can move on to chapter 2. We're going to 2.1. Chapter 2, the focus is first order. First orders we have to deal with on their own, because things of second order and higher, they all actually work familiarly. First order kind of has its own little quirks. So we're going to do first order, I'm going to do second order, and then once I teach you second order, it's going to be very natural to increase that to higher orders. And so after second order, I'm just going to do higher order. And here we're talking about linear. Well, not necessarily linear. Sometimes it's linear, sometimes it's not. I'll tell you when I'm specifically mentioning linear. I'm actually going to start by mentioning that first order linear ODEs. So that's the first topic in chapter 2. Let me tell you what that is. I know sometimes is going to be ridiculous how narrow of a thing we're looking at. But we get some useful techniques out of it at the end of the day. Pretty soon we're going to look at second order linear with constant coefficients versus second order linear when this coefficient looks like an x squared and that looks like an x, and there's a second order linear when this coefficient has this particular form but not that particular form. It can get pretty crazy. Right now we're going to do first order linear ODEs. Now these have a very nice and simple form. The first order linear ODE is an equation. And when I say off the form, let me just write out here, that can be written in the form. And here's the form of a first order linear ODE. We assume it looks like y prime, so it could be dy dx or dy dt, plus p of x times y equals g of x. That's it. That's a first order linear ODE. Anything that you can put in that specific form is a first order linear ODE. Notice that here p and g are, I can assume they're just general functions of x. There is no requirement on what they should look like. However, the y's have to behave in this particular way. I could have a y potentially multiplied by some function of x. I could have another function of x that's sitting by itself over there, and I can have a dy dx here. Now this here, by the way, is called the standard form. And this is used throughout. So even with second order and etc., the standard form is usually going to be the form where the coefficient of the highest thing is 1. Right? So that's going to be a thing. That's going to be a running theme. And in the event that it's not 1, all you have to do is divide through by that thing. And if you create any points of discontinuities, they're actually important to pay attention to. But this is the standard form for a first order linear ODE. Now it turns out that we actually know how to solve these guys very well, at least in theory, provided that the integrals are nice enough for us to calculate. So, let me show you how to actually do one. This is a first order linear ODE. Now, of course you can appreciate it doesn't exactly look like this, but I want you to realize that I can make it look like that easily by just dividing through by ln, right? Now, as long my x is greater than 1, which means the ln is never going to be 0, so I can just divide through by ln without any consequence. But at the moment, I am going to refrain from doing that because I see a nice little thing here. I realize that this here is actually y times ln x all prime. Did you notice that? Did you guys see that? No. Did I move too fast? Product rule, right? Do the product rule on that. What do you get?
Yeah, you do that.
You get that, right? Okay, so we're all cool. All right, moving on to the next kind of ODE. Okay, no, we can finish this. Let's finish this. So this equation becomes that. Very convenient. That's awesome. And we can finish by integrating both sides. Fundamental theorem of calculus is going to tell us that this is going to kill that. And so here we have y times ln x equals e to the x plus c. And so I can solve for my y here as e to the x over ln x plus c over ln x. And that is the solution. And hopefully that was clear to everybody. We can. So you guys try. Do this one. Okay, do that one. I'll give you guys a couple minutes. Okay. What do you think happens here?
Well, the e to the negative 2t definitely has to get turned into 1 over e to the 2t, right? And then you can factor that out.
It's not separable.
Is it separable?
Multiply each side by e to the 2t.
Yeah.
Okay. And what would happen?
That's product.
You start with that.
Yeah.
You
Flip
multiply
that 1 over
e to
e.
the 2t to the other side and it'll cancel it.
That was still product.
If you notice that that's also the product. That's the
It's also the product rule?
yeah.
What do
Because
you
if
mean?
you do if that you just change that to 1 over e to 2t, it's easier to see.
Oh, well, this is actually,
It's a-
well, this is e to the minus 2t dy dt minus 2 e to the minus 2t y equals t
I
squared.
did the opposite.
Yeah.
I turned
Yeah,
the other one.
yeah.
I flipped the first one.
And
Yeah,
this guy is what? It's the derivative of that, right?
Yeah.
So that's actually the product rule again. So that would be e to the minus 2t times y. It's all prime.
Wait, was the power again?
I was getting.
It was the product rule again, yeah. You were looking for something different? You think I spring things on you guys?
I
Like,
think
no.
you throw rock twice.
Expect the unexpected, and maybe I'm gonna keep you guys on your toes. Integrate both sides. This is just gonna become e to the minus 2t times y. That's going to become t cubed over 3 plus a constant. And so my y is going to be e to the 2t t cubed over 3 plus c e to the 2t. And that's the answer for this one.
Let's say
Yes.
if you were to factor out the e to the 2t, because that's what I thought at first, would you be able to do
Oh,
anything?
yeah, you're right.
Sure.
Because then like you take out the fact and then you multiply to both sides,
Yeah.
and you get e to the 2t.
So you would get y prime minus 2y equals t squared e to the 2t. Something like that.
Would you be able to do anything with that?
You tell me, could you do anything with it?
I had that, I couldn't do nothing with it.
E to the 1 over.
Because it's not separable.
Is
right?
there a way to know, like immediately, or is it really just trial and error? I've been meaning to ask.
Well, you don't see what's going
No,
on.
I understand, but I'm saying like,
Any questions about these
I had to get
questions?
stuff to know that it wasn't separate.
I have seen it from
Yeah. What?
I have a hard time seeing it from, like, I can't make that connection from the first line to seeing that it's a derivative.
Because it's a pattern that I showed you guys. I said, here's one where it looks like the product rule, and then here's another one that looks like the product rule. Now you do it. Now, here's a question that I would ask. Does that always happen? Is the left side always the product rule?
No, can't be.
Like, no way, right? There's no way that always works, right?
It does?
Let's go back, right? Now, I know that was a little mean, but that was a very important lesson for you guys. Because you go far enough in differential equations, this feeling will hit you all the time. Some dude is going to tell you, oh, you just saw me do it this way. And you're like, how the hell did he see that? How did you come up? Where did that come from? And there will be no answer. I just saw it. And that's literally the best answer you can ever get, right? So embrace that feeling of not really knowing, what did you do? Well, yeah, I see what you did, but how did you know to do what is going on here, right? That's differential equations, okay? That's a part of it. Sometimes you have a pattern, some smart dude say, hey, that's the product rule. Hey, you're right. Yeah, that is the product rule. However, first order linear differential equations are super special and they're super nice in the sense that you can always get something like that to work, even if it's not given to you. Okay, let's actually look at it. What do you need for the product rule to happen? Right? So if you have f and g, this is f prime g plus, let's use f and y just to be suggestive. So it would look something like f y prime plus f prime times y, right? Anything that looks like that I know is the product rule, right? So that's going to be a pattern that I can see. Now the question is, does that pattern always show up? And the answer is no. However, the message of hope is you can force this situation. And let me show you how we're going to force this situation. Given y prime plus py, and of course I'm assuming that it's not p of t or p of x or whatever. I'm just not going to write it all the time. Now here, just remember, because I don't want to write all the time, p and g are functions. They're not constants. Of x or t or whatever. Okay? Here's something that you can do if you have something in this situation. We're going to find a function mu. There we go with the Greek letters. Right? So that if we multiply the above, the left side becomes the product rule. And you're like, there's no way that we can always do that. Can we always do that? In theory, yes. And here's how it's going to work.
Is it like substitution?
Hold on. say I have y prime plus p of y equals g. What I'm going to do is I'm going to multiply through by this function mu. Right? This mystical function that we don't even know any. What do you mean a function? Just hold on. There's going to be a function that gets this to work. Okay. Now, if we want this to be the product rule, what is the pattern? What do we need to happen for this to actually look like a product rule?
We need some function f followed by the derivative.
Yeah, but specifically with these letters here. Tell me what I need to happen here.
You need the derivative of p.
I need the derivative of what?
P.
Why do you need derivative? This thing here needs to be the derivative of mu, right? Because that means I have mu, differentiate the y, plus leave the y, differentiate the mu, right? That's the product rule. So in order to get this to work, we need that mu prime must be equal to p times mu, right? But what's that?
It's its own other thing.
That's a first order separable ODE.
Oh,
So in order to solve this ODE, I end up having to set up a smaller ODE that's going to help me solve that ODE. So we're going to be like Thanos, we use the stones to destroy the stones. I'm going to use a first order ODE to conquer this first order ODE, and it's just like Inception, you're going to go in. Okay, so what would mu have to actually be in order for that to work? Well, like I said, it's separable. So this means that d mu dt is going to be p times mu, and I'm going to separate the variables. So this means d mu over mu is going to be equal to p dt. Now remember, this is a function, it's not a constant. And so this means that ln of mu is going to be equal to whatever the integral of p of t dt is. We don't know. Now, any integral will do because ultimately we're going to go back to the derivative and the constant is not going to matter. So I'm going to choose the plus c to be 0 in this instance. And so if I were to solve for mu, what would I get? Mu must be equal to what?
E
To the integral of the p of t. Given a first order linear ODE, I can always create the product rule on the left side by multiplying by that guy. Take the coefficient of y, integrate it, throw it in an exponential. That function will make the left side the product rule. Once the left side is a product rule, I collapse it and just integrate both sides. So here's the method. And by the way, this is the mu in this case is called an integrating factor. Why? It's a factor that we multiply through by that's going to allow us to integrate things nicely. So now I can describe to you what we call the integrating factor method for solving first order linear ODEs. Now, as long as in theory this integral can work out and the resulting integral I'm going to have to do after doing that guy, this will always work theoretically as long as the integrals are nice. So, here's the integrating factor method. Solve y prime plus p of t times y equals g of t. Given y prime plus py equals g, 1. Multiplied through by mu equals e to the integral of p. So you have to put it in this form if it's not in that form. Take the coefficient of y, create that number, or that function, rather. this will result in the following scenario happening. That was what I need to let P of mu be mu prime, which means that the equation can now have a new form. The equation will have the form mu times y all prime on the left side. We literally force that to happen. We solve for the specific mu that makes that happen. Equals, of course, on the other side, you're going to have the mu times the g. The third thing you're going to do is, of course, now you're going to integrate both sides of this guy. So you're going to have the integral of the mu y prime equals integral of the mu g. Now, of course, fundamental theorem of calculus implies that that side is going to be mu times y equals to the integral of mu g. Now, I have to keep these as an integral because I really don't know what it's going to end up looking like, right? Because it depends on what the actual functions look like. And then I can just divide through by mu. Of course, this integral here is going to have a plus c associated with it, and so we're going to end up having c divided by mu. Now, you have a couple ways to do this. You can actually memorize that formula and always use it, or you can memorize the process and do the process. That's what the solution is going to look like. That is set form. So first order linear ODEs are remarkably easy, at least in theory.
Is there any advantage to doing the entire process, or should we just remember the process?
Advantages. For the class, no, not really. But for your mathematical maturity and long-term health and well-being, yes.
Okay.
So,
Now, I have a quirk. I don't like memorizing stuff. So a lot of the times, I memorize the bare minimum and I learn to derive everything else I need on the spot. I only memorize if it's going to take forever for me to derive. And just, that has helped me in math so much. Like, I just get used to math so well now because I'm always deriving everything. Everything I do, I derive it. Right? So when everyone's just like memorizing, not knowing where everything's coming from, I'm figuring things out. And that builds on itself into the future. So technically no, but probably you should.
Okay.
Even when I'm doing this, I never use that formula. I always do that. But the thing is, I can do it so quickly that I don't really lose much time over it, you know? So let's just say going through the motions is optional, but highly recommended.
No, I definitely see the value of it.
Let's actually do some examples. First one, y prime plus 2 times y equals e to the minus 3t. Y prime minus 2xy equals x. Let's make this one an initial value problem. Make sure you know how to deal with those. T times y prime plus 2y equals sine of t. This is an initial value problem. And let's make the assumption that t is greater than 0. D. Over x dy dx minus 2 over x squared y equals x cosine x. So, to to speak to the earlier comment, in many ways, especially when you're doing differential equations for the first time, it's going to seem like the mathematics of hindsight. So there are going to be many times where we're in certain situations, and I'm going to say, pretend there's a solution that looks like this, right? Why? Just pretend. We're going to actually use that to solve the problem. And then we're going to say, see, there's the solution, there's the answer right there. And like, how do you know that works? You literally just pretended it was the answer. How do I know it's actually the answer? And it turns out that because the differential equation is going to work out that nice because there are two really hugely powerful theorems. And one of them is the existence and uniqueness theorem. So basically there's going to be some sense in which if a solution exists, it's unique. Which means if my pretend solution actually works out, then it is necessarily the correct solution. Right? So then it's going to be like, we can just guess something that's convenient that we know how to work with. And if it works out, it's actually good enough. Right? So there are going to be a lot of times where I'm like, oh, let's take advantage of this pattern. And you're like, where did you get that from? It works. And you know what? That's good enough for differential equations. Because it turns out, if it works, it's the right guy. I don't need to look for someone else. I don't need to do anything else. It's the right guy. Right? So we're going to predict how many solutions there will be to a given differential equation, and we're going to predict how unique they are, and we're going to look at how we can know that we found all of them, and if the ones that we found are the right unique ones. So over the course of the semester, I'll be doing this. So that little exercise earlier is just to get you uncomfortable with that feeling. That sometimes just, hey, someone realizes that this works. And then in hindsight, they prove, yeah, that has to be the only thing. So a lot of differential equations are like that. We're going to just, oh, pretend the solution looks like this. Why would you do that? Because I know how to deal with that case. Okay. Hey, it works out. And there's this theorem that tells me that's the answer. So.
But there's going to be clues within the functions of the
Yeah, and for some of them, it'll be a little bit intuitive, and I'll point this out when it happens, but then other times there'll be no reason why someone will do it, and I'll tell you when even I'm not sure why they decided to do that and why it worked out. But sometimes you're going to see that it might make sense, and that might help you to someday choose something that looks random to everybody else except you, and it's going to work out and you'll be fine. Okay, let's get through these. We don't have much time left, and I probably want to start the next lecture with a new section. So again, I put a lot of practice problems in the syllabus, so you can practice from the textbook if you want, as well as I'll post a web work homework so you can get more practice on these. It is something that you're going to have to get used to, but like I said, it's a process that's fully laid out for you and you kind of know where it's going to lead to. So yeah, here's y plus 2y equals e to the minus 3t. Notice here that this is in standard form. Notice here that this is the p. So what I'm going to do is mu is equal to e to the integral of 2 dt, which is going to be e to the 2t. What I'm going to do now is I'm going to multiply that equation through by e to the 2t. Now, because I know what's going to happen on the left side, I'm going to skip the step of showing that. I'm going to literally just jump here and write this is e to the 2t times y all prime. Right? Because if I multiply this by e to the 2t, you're going to notice I'm going to have e to the 2t plus 2e to the 2t here, which is the derivative of the other. It's going to work out. We already saw for it to work out. But multiplying this by e to the 2t gives me e to the minus t. Right? So now I can integrate both sides. Come again?
E to the minus c, how do you get that again?
addition.
Oh,
E to the 2t is the integrating factor, so I'm going to multiply everybody by e to the 2t.
oh.
So this will become e to the 2t, this is going to get multiplied by e to the 2t, this is going to get multiplied by e to the 2t. Now over here, 2e to the 2t is the derivative of e to the 2t. So this ends up looking like a product. So this whole left side collapses into this. It's always going to be mu times y all prime, always. We literally solve to force that to happen,
Yeah.
right? We use the differential equation, we use the mini differential equation to force that to happen to the bigger differential equation. So that's always going to happen. So I know that's going to happen. So I just jump down here and write this. Multiplying this by e to the 2t, add the exponents because laws of exponents, and now we get into a situation where we can integrate both sides. The integral of e to the minus t is minus e to the minus t plus c, and now I can just divide by e to the 2t everywhere. So this becomes, that's the solution. If you don't believe me, you can check. Take that derivative, then multiply that number by 2, and you'll see that you will get e to the minus 3t is a result, if you add them together. Let's look at it. Okay, someone else tell me quickly what we're going to do here. What do you see? What are we doing?
P is negative 2x.
Right? That's our p, so what do we do with it?
Find mu.
What's mu?
E to the integral of e to the
That's going to be?
E to the negative x squared.
Okay, now that you have that, what happens?
You like.
So what's the left side?
y times e to the
Y times e to the negative x squared, all prime. It's going to be that guy times y all prime, always.
Equals x times e to the x squared.
X times e to the minus x squared.
You take integral.
Right? Now, integrate both sides. And we're out of space. Now, what's the integral of the right side? Huh? No, it's not by parts.
What was it again?
It's over here.
Oh.
X times e to the minus x
Oh, yeah,
squared.
your substitution.
Substitution, u equals minus x squared. You're going to end up with minus 1/2 e to the minus x squared plus c. And now I just multiply both sides by, or this is divided by e to the x squared, so I can multiply through by e to the x squared. So this means I have minus 1/2 plus c e to the x squared. Right?
Yes.
Now, don't forget we were given an initial condition, which means it is not good enough that we have this c here.
We have to solve for c.
We have to solve for c, given our initial condition. So given that y of 0 is 0, this means if I plug in x equals 0, the y value is 0. So since y of 0 is 0, this means, so the 0 in here is the x value, this here is the corresponding y value.
So c equals 1/2.
So 0 is equal to minus 1/2 plus c equals 0. This means that your c is equal to 1/2. And so now finally your solution is going to be
Negative 1/2 plus 1/2 e squared.
And this is the particular solution. It solves that differential equation and it passes through the origin. Let's do it again. So you want to do these until you're just bored doing them, where they all start to morph and look kind of the same. Where it's like, okay, yeah, there's a little integral on the right side that I might have to deal with, but I'm an expert calc too, so it's fine. That was C. It's out of order. Or was that B?
B.
This y prime plus 2y equals sine t. Okay, what do we do here? Ah, you have to divide by t first. Remember, you have to be in standard form. So that is not good enough. So the first thing you're going to do is you're going to divide through by t. That is your p. Okay? So you have to remember the standard form because the procedure works on the standard form. So now what I'm going to do is mu is going to be e to the integral of p. This is going to look like, well, that becomes ln, right? So it's e to the 2 ln t, which I can write as e to the ln of t squared. Now technically this is that, but we said that the t was positive. Yeah, so the absolute value is the same as the normal one. Now that cancels, you just have t squared. So what's going to happen is, this is going to become, now I'm focused on this one. So now, forget about this one once we're in standard. I'm focusing on this one. The left side is going to be t squared y prime. The right side is going to be t squared times this. Now I'm going to integrate both sides.
You need by parts for the right one.
Need by parts for the right side. So this is going to be t squared y equals,
I gotta just remember that. That's such a common one, I feel like. T sine t or t cosine t.
Yeah.
Exactly. You gotta set t equal to u, then
Yeah.
du is dx, then
yeah. The integral of that is minus cosine. Integral of that is minus sine. So this is actually going to be equal to minus t cosine t plus sine t. And so now this is going to mean that our y is going to be, now I'm going to just divide that by t squared. That's tabular integration. It can make integration by parts easier. I mean, it's kind of overkill for this, but you couldn't bother writing down.
what did you call that?
Tabular integration. Huh?
I said you make a list and you make a bunch of arrows and then the answer pops up.
Oh, yeah. I taught it in my Calc 1 and Calc 2 classes in the earlier semester, so you just look up those lectures and see the lecture. It's really convenient.
It either has to be an exponential or a true function?
No, once integration by parts works, we can get that kind of scheme to work.
Huh.
But if you have like some kind of infinitely repeating one that you can't
I still can get it to work.
Really?
Yes.
It's after the second.
It's
round.
called
It's
magic.
not okay.
It's not magic, it's tabular integration. Where?
You get the same thing again.
Huh?
Then you gotta divide.
Did I give a thing?
Yeah.
I did. Okay, so we did say y of pi over 2 should be equal to 1. So basically this means 1 is equal to, what's cosine of pi over 2? 0. Plus, what's sine of pi over 2? 1. And the t is
2 over 5.
pi over 2 squared. And
Plus c over that.
plus c over pi over 2 squared. So this means I have 1 equals 4 over pi squared plus 4 over pi squared times c. And so my c is going to be equal to 1 minus 4 over pi squared divided by 4 over pi squared equals that.
Okay, yeah, that's it. Nice.
And so my y defined is equal to minus cosine of t over t plus sine of t over t squared plus pi squared minus 4 over 4t squared. That's a particular solution.
That was quick.
And the last example. Yeah, like when I'm writing a test, that's how much time I think in my head that everyone needs to take. Oh yeah, the 2 minutes, yeah, this is 2 minutes, that one's 2 minutes. Oh yeah, this is definitely a fair test.
Should I just be doing tabular all the time for this class, to be honest?
No, tabular only works with integration by parts.
No, I know, but I'm saying for integration by parts for this
Yeah,
class.
you can always use tabular.
All right, that's great news, thank you.
There's the thing, people always forget that there's a tail end to the tabular. That deals with the infinite repeating case.
Really?
Yeah.
Okay.
Like no one, you didn't even know there was
I
a
had
tail
no-
end to it.
I didn't know that
There's
existed.
you go down, 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 and then you come across. But usually, because that across is a 0, everyone just says, you don't have to worry about it. But when it's not a 0, it becomes something that you have to deal with.
I know what I showed you. Everything that the world
Yeah, like x to the 5th times e to the x. What's the integral? You can do it in like 30 seconds with that. Maybe less. Okay, last one. I'd show you now, but we're already out of time, so I don't want to keep you guys too long. Even though I probably have more reason to get out of here than most of you. I teach at several places, and so everyone has this like Monday schedule thing to make up for the Monday.
Oh no.
On different days. I've had like 3 Mondays this week. Like I'm so over this week. I want to get out of here faster than you guys, trust me. So I'm not going to give the tabular lecture right now. We're moving on. Okay. So, what do we do here? Multiply through by x because we need standard form for this method to work. So I'm going to multiply by x the entire equation. So that's going to give me the y prime minus the 2 over xy equals x squared cosine of x. And so now, what do we have?
2 over x is p?
P is the 2 over x.
Negative 2 over x, sorry.
Negative 2 over x. This means that mu is equal to e to the integral of minus 2 over x. Well, that's just e to the minus 2 ln x.
So it's x to the negative 2.
So it's just x to the minus 2. Right?
Oh, yeah.
And so now what you're going to do is you're going to multiply that by x to the minus 2. Right? The standard form of the equation. So you're going to get x to the minus 2 times y prime equals
X cosine of
cosine. Integrate both sides. And so we're going to have x to the minus 2y is equal to positive sine x plus c. And then we multiply both sides by x squared. So our y is equal to x squared sine of x plus x squared.
Because you multiply the right side by x and the other side. Except for x and the other side.
And that's something you now know how to solve. Linear first order differential equations. That's the method. It's called the linear, the integrating factor. So now we know 2 classes of things, the separable kind and the linear first order kind. Now we know how to solve 2 kinds of differential equations. For once I don't divide by 0 or something like that. as well as making the absolute value nice. Because it could be less than 0, then I have to keep the absolute value for about makes greater than 0, so the absolute value I don't have to worry about. Let me stop this.